All right, let's go ahead and get started here. Some of the slides I think are a little bit off center, but I'm not going to let that bother me. I think the content's still there. So good morning. Welcome to the Breakfast Bash. Today we're going to be talking about something a little bit more theoretical than previous ones. All of the focus on the previous Breakfast Bashes has been on data structures and sort of an algorithm associated with that data structure. But with the last one that we talked about binary trees last week, and I started to realize that it's sort of difficult to talk about data structures and their algorithms without mentioning sort of the reason why we care. And typically the reason that we care about data structures in the first place is because it makes some task either faster or more memory efficient. And there's a very sort of easy intuitional way of talking about that, and I'm going to try to detail it in as much detail as possible in today's Breakfast Bash. The concept is computational complexity, and basically what you want to find out is how good a function is. In our case, we want to figure out how good the algorithm is. So we've been talking about these algorithms, and we want to know how good the algorithms are. But sort of, what does it mean for an algorithm to be good? Well, on one hand, you want it to be fast, and on the other hand, you want it to be space efficient. So we have sort of one unifying concept that can sort of tell us about the speed and memory efficiency of algorithms through some analysis. And you'll probably see this pop up all over the place if you do your own sort of digging into data structures research. And if you're a self-taught programmer, you've probably also seen this concept before, just when looking for random solutions to whatever. It's a concept that pops up everywhere, and it's nice to know about. I'll preface this whole thing by saying that this is very theoretical, and even if you don't understand everything entirely, I just want to kind of make sure that everybody understands the sort of intuition behind these concepts, because in the future, I'm probably going to be using computational complexity instead of hand-wavy arguments to describe the efficiency of some of the algorithms that we're going to talk about when talking about more complicated data structures. So with that, we'll move on. The concept is Big O. Big O is a way of expressing the speed at which a function grows. And the informal definition, the sort of hand-wavy definition for Big O notation, is that if you have two functions, f of x and g of x, and f of x grows at the same speed or slower than g of x, then we say that f of x is Big O of g of x. More specifically, Big O of g of x is it's a set of functions. And if f of x is Big O of g of x, f of x is inside that set. That's sort of what it means at a more mathematical level. So why do we care? We care about the growth of functions because we care about how algorithms perform relative to the size of the data set we're working with, in both speed and space, which I talked about earlier. Growth of a function measures this stuff very well. So if you see that as the size of a data set is getting bigger, it starts to grow more quickly, then you know that when your data set starts to get very large, you're going to have some issues processing that data. Specifically, so say here, we'll walk through a short a short example, which might actually make this a little bit clearer. But essentially, we don't want our data set getting bigger to negatively affect our algorithm enormously. And so the slower the function gets slower, so to speak, the less of an effect the size of the data set has on the speed of the algorithm, the better it is. So here's a simple example. So let's say we talked about singly linked lists the first breakfast bash, I think, or maybe actually it was like the third best breakfast bash of mine. And so what happens if we want to iterate through the list? So we want to do something with each of these nodes here. We want to visit 0, then 8, then 2, then 5, then 8, then 1, then 19. And we want to do something with each one of these nodes. So this is an algorithm. Basically, walk through this list. And this algorithm is, we can put this into terms of big O, and when we're talking about the speed of the thing. And we can say that f of n is the iteration algorithm that we're going to be using. So whatever that visiting was. G of n is actually just n. So so it's just the constant function n. And we can say that f of n is big O of g of n because f of n grows. The iteration algorithm goes as fast. Its speed is proportional to the size of the list, if that makes sense. So we have to visit 1, 2, 3, 4, 5, 6, 7 nodes. That means that it's going to take us like 7 time units or whatever to process the thing. If we add an extra one, it's only going to go up to 8 time units. And we'll look at something in contrast to this later, but basically that's a pretty good algorithm. You're not gonna, there's no real way to make that any faster. You're gonna have to visit all the nodes if you want to iterate through a list. But the fact that when you tack on an extra node, you aren't adding like a ton of extra time to the speed of the algorithm. That's a good thing. And that's sort of what we want to talk about. So from here, I actually want to move on to the formal definition, and this is what the meat of this is going to be. I kind of want to take like a theoretical detour here, just so that hopefully this idea bubbles up into some sort of intuition about how the speed of algorithms relative to their size works. And the formal definition of big O notation is basically a function f of x is big O of g of x if there's a constant n and a constant c, and by constant I mean a number that does not change, such that the absolute value of f of x is less than or equal to c times the absolute value of g of x for all x greater than n. So that's a mouthful. And so we're going to walk through this kind of with pictures and sort of step by step so that it doesn't all just, get lost. It does take some staring at to understand, and I kind of want to make that a little bit easier. So what does this mean really? So let's say we have two functions. We have g of x here, and we have f of x here. And these are just graphs of how the function grows. This is a function, this is a function, and these are the functions graphed on a graph. And they're color-coded so that we can talk about them. So I've color-coded them in the definition here, and there's a little, whatchamacallit here, a legend. So let's remove this constant to begin with, this constant c, because I think this is the source of a lot of confusion. Like, let's just limit c to 1 and see what happens. So if we limit c to 1, then we completely get rid of that c term here, right here, right before g of x here. If f of x is less than or equal to c times g of x and g of x, and c is 1, then we just have f of x, the absolute value of f of x is less than or equal to the absolute value of g of x. And we don't need the second constant c right here. We don't need that anymore. And so now the question becomes, is there a constant n such that the absolute value of f of x is less than or equal to the absolute value of g of x for all x greater than n? And lo and behold, we've got that here. Sorry, the slides got cut off here, but this is n right here. So you can see at this point, f of x is always less than g of x after this point, and that's the point. So we just wanted to find some constant, some number, which happens to be right here, that every point after this one, and we're assuming that like this trend sort of goes on to infinity implicitly, but at this point, f of x is always less than or equal to g of x. And these absolute value things here are basically just to account for like what if f of x was negative, like completely negative. It's still sort of growing quickly. It's just growing downwards, and we want to account for that. Although it doesn't necessarily matter in the context of computer science, so you can sort of not even worry about the absolute value and just think about it this way. But anyway, so yeah, we can see that g of x clearly at some point grows more quickly than f of x, which is exactly what we want. So we say that f of x is big O of g of x. And in literature, a lot of times it'll say f of x equals big O of g of x. I do not like that. I don't like that notation at all because it's a huge abuse of this equals operator. F of x is not equal to big O of g of x, but that's often how you'll see it. More accurately, f of x is in the set big O of g of x. That's what this little symbol means. But historically, it's written like this, and it's always bothered me. But you know, just so you know, the really big O of g of x is a set, and f of x is inside of it. Oop, sorry. So let's talk about that constant. It's pretty easy to see in this graph that at this point, everything after here is less than everything after here. Like f of x is less than or g of x after this point. But why do we even need that constant, right? But why can't we say that since g of x is always greater than f of x, like you'd almost expect this to always happen if a function grows faster than another function. Like g of x is growing more quickly than f of x, therefore there's a point where g of x is, you know, always going to be greater than it. But let's switch up f and g, and this is kind of the situation where you want to talk about that. So the key is that if the functions are equal or at least tend towards the same point at infinity, functions, they don't necessarily ever have to cross paths, but they can grow at the same rate or at relatively the same rate. So in this case, so we have these two functions, and they tend towards the same, like they are, for all intents and purposes, like running, they're the same function shifted up by a constant. Like f of x is shifted up by some number of units but they're growing at the same rate or relatively the same rate. But we still want to show that f of x is big O of g of x. That is to say, f of x is big O of g of x. But there's no point where these things cross that we can say, oh, okay, yeah, f of x is less than g of x for all x past this point. It just isn't true. They're never going to cross because they're just not. They're parallel functions. The functions grow at the same rate. So what do we do in this scenario? Clearly, they're growing at the same rate, and that's kind of what we want to measure. So what do we do? So if you guys don't remember from middle school or high school or whatever, when you take a function and you multiply it by a constant, it shifts its slope. So if we take g of x and we multiply it by, here I'm saying that's 4 times g of x, it moves its slope up. So at every point, it goes proportionally higher. So now let's look at the modified graph. If we overlay 4 times g of x onto this graph, there's obviously some point here that looks a lot like the point that we saw in that previous slide, where we were trying to look at f of x and g of x and figure out whether or not f of x was big O of g of x, and we had all those squiggly lines. Here we've just got 2 straighter lines, but we can, when we multiply g of x by 4, we get f of x is less than or equal to 4 times g of x for all x greater than or equal to n. And this is n here. Again, it's cut off. But yeah, so this is our point n, and now we've satisfied this. And that's kind of why we need that constant. We need to know if 2 functions are linear and they grow at relatively the same rate, we want to consider them to be semi-equivalent in this sense. Like we want to say that f of x is big O of g of x if they're both linear, or if they're both quadratic, and so on. So yeah, we're good. All we have to do is substitute c for 4, and we've got this graph, and now we have all of our bases covered. F of x is big O of g of x. So I want to sort of back up a little bit at this point. That is the full discussion of like theoretical big O notation. If you didn't understand all of it, don't worry. I'm not a math professor, and I recognize that. So if some of this kind of is a little bit muddled or confusing, feel free to ask me about it, or do a little bit more research, or not even worry about it. Really, what we want to develop is an intuition about, well, why we care in the first place. I just wanted to kind of take this aside because I think it's helpful to understand the nitty-gritty about everything, and I thought it might be interesting. So the point is that we want to develop an intuition about the relative time and memory usage of an algorithm. When we're talking about data structures, we want to understand how quickly they can perform a specific type of algorithm. And that's why we use data structures. So counting the elements in a linked list. Let's say we want to count the elements in a linked list. It requires that we visit each node exactly once. So like we saw earlier, the algorithm is big O of n in speed. But since we only ever have to keep one node in memory at a time, as we walk the linked list, we just look at the node and tack it onto a sum. Tack 1 onto a sum, I should say, or a count. We only ever need to have one thing in memory at any given time, and so it's big O of 1 in memory. That's sort of the intuition there. We have to walk n things, so it's going to take us n time units in speed, ish, but we only have to keep one node in memory at any time, or a constant number of nodes in memory at any time. So it's big O of 1 in memory. But what if we wanted to compare all of the elements in the list to all of the other elements of the list? So I'm just going to skip on to the next slide so I can show you what I mean, because the wording that is a little bit confusing. But what we want to know is how many times do we need to compare if we're taking each element of the list and comparing it in some way to every other element of the list. So for every single element. So we want to compare 0 to 8, we want to compare 0 to 2, we want to compare 0 to 19. We also want to compare 2 to 8, and 2 to 1, and 2 to 19. And so what we can do is, it's kind of common, we can start here, iterate through the list, and then move on to here, and then compare that with everything, and then move here, and then compare that with everything here. And that way we're going to end up comparing all the elements. So if we're starting at 0, we need to compare 6 things. We're just going to do like a little bit of short analysis here on how much we need to do, how much work we need to do in order to accomplish this goal. So first we have 6 things. We move on to the next element. We've got 5 things to compare. And we're going to keep doing this. We're going to keep stepping through the list and comparing it to all of the elements after it, until we get to the last element and we have 0 things to compare. And so that produces this nice little graphic here. We've got 6 things to compare at the first node, 5 at the second, 4 at the third, and so on. So if you look at this, we've got 7 total elements in the list, and we're summing everything from 1 to 6 in order to get the total number of comparisons that we're doing. This is sort of a side note. There's this quip about how Carl Friedrich Gauss, a mathematician, he was tasked with like some busy work in elementary school, and they said sum the numbers from 1 to 100, and he came up with the solution very quick. I think it's like 5,050, and his teachers were like, "Wow, what, you know, how'd you come up with that so quickly?" And he said, "Well, if you just take like the first number and the last number, and you pair them together, and then the second and the second to last number, and pair them together and whatnot, you end up with this formula that basically says the sum of the numbers from 1 to n is n times n plus 1 over 2. So this gives us a general formula for how many comparisons we're going to have to do, because if we take n to be the number of nodes minus 1, then we get, in our case, 6. Then we just take the sum from 1 to n minus 1. And so in our case, we have 6 times 7. We want to sum the numbers from 1 up to 6. So we're going to take 6 times 7 divided by 2. So that's n times n plus 1 divided by 2. We get 42 over 2, which is 21. And we get 21 total comparisons when we're talking about a list of length 7. But in general, we have this general formula. This is just expanding out this thing into, we're just going to multiply n by n plus 1 and divide by 2. We get this formula here. So I just pulled out the fraction, and then n times n plus 1 is n squared plus n. And when we're talking about big O notation, there are a couple of tricks. Basically, you can ignore this constant here. You can ignore any constants with big O. So we just drop the 1/2. And we can also drop the non-leading terms. So non-leading terms are terms that don't have the number, like that aren't of the same exponent as the highest exponent, if that makes sense. So in our case, n is a term. It's not n squared. It's not n cubed. It's just n. We can drop n as well. And so in literature, if you're reading up about algorithms and you find the algorithm how to compare each element of a list with every other element of the list, you're very likely to find this algorithm somewhere where you just walk from left to right and iterate over the remainder of the list and compare with each thing, you're probably going to see that that this algorithm is big O of n squared in speed. So you're going to have a big O of n squared comparisons. That's all it's saying. And hopefully these couple of examples along with the mathematical analysis can kind of give you a little bit of intuition about what this means at all. We are just concerned with how good an algorithm is, essentially. Like I said at the beginning, we just want to know how fast an algorithm is as the data set gets bigger, and how much memory it uses as well. And that's the point. So thank you. I know this one was a little bit longer than normal, but thanks for sticking around, and I will see you next week, and we'll get back to the previous format of talking about data structures, but I'm probably going to sprinkle in a little bit of this big O notation. So I just wanted to have a short kind of break from that stuff so I could say it without worrying about hand waving my arguments. So thank you.